Hey everybody, Dr. Retzig here with you. This is our third video in Chapter 15. It's about Section 15.3, which is very short. It could have been embedded in 15.2 and even is embedded in 15.2 in some books. It's all about area and average value. Let's get started. So the idea is this. If you have a region flat in the xy plane, like this, say, and you're interested in the area of that region. So we'll shade it in like we do sometimes. Here's the region, and we want to find its area. You have tackled the area problem in calculus of one variable, and we just want to see it as a special case of what we've been doing in section 15.2. So here's the idea. What if you imagine a surface floating above your region at constant height 1? So in other words, just a horizontal sheet at height 1. So maybe directly above our region, maybe it looks like this, where this is directly 1 unit above there, and this is directly 1 unit above there, 1 unit, 1 unit. So this is z equals 1, constant height 1. Well, on the one hand, if you wanted the volume underneath that surface at height 1 and above the region R, then according to 15.2, you should do the double integral over the region R of the function 1 with respect to area. Yeah, that's true. That's great. On the other hand, the volume of that 3D solid object, so let's say we wanted to shade it in like this object, the 3D solid object consisting of all points in 3D space above R and below the sheet, that object, I guess there's some more right here, huh? That object, its volume is area of the base times height, but the height is 1. And so the volume is simply the area of the base. Therefore, if you are interested in finding the area of some region in the xy plane, you simply have to do the double integral of the constant function 1 over that region. That's it. That's 15.3 in a nutshell. So 15.3 is designed to make this observation. Anytime you want the area of some region, simply double integrate 1 with respect to area over that region. And honestly, even in the very notation itself, if you think of these as S's for sum up, and you think of these as an actual product, and you think of dA as a tiny bit of area in R. So maybe dA is like a tiny little rectangle like that down in R, then even the symbolism, it looks right. 1 times that tiny bit is that tiny bit, and if you add up all the tiny little bits, so there's a tiny bit there, and a tiny bit there, and a tiny bit there. If you add up all the little DAs, what do you get? Grand total, you get A. Okay, so there's nothing super deep or exciting in that box, but it can lead us to one idea that is valuable. And so to wrap up the video, we want to think about what that one added value idea is in 15.3. To think about it in several variables, let's first think about it in one variable, as we often do. So if you had a function like this, so this is good old xy coordinate system. That's y equals f of x. It's happening over some region on the x-axis, say there to there. The area under that curve comes out to something. So if you were to go and compute this like we do in Calc 2, that gray area there, it comes out to something. Can you imagine a competing picture on the right where the function is not interesting and curvy like the one on the left, but is constant, where the area is the same over that same region? So I'll put the region in again. Here's the region. What if we put that constant function in, say y equals c, over that same region, in such a way that the two areas matched? Now, the area we're shading in at the moment on the right, that's easy to find. It's just c times the dimension of the base, because it's a rectangle. If you were to draw a little line across the areas would only match if this bit here that fell short of the line agreed perfectly with this bit here that was above the line. So it's almost like we took a bulldozer on the picture on the left and used the amount of earth above the dash line to fill in the amount of earth below the dash line so as to keep the grand total area the same. Now that value right there, there's a word for that. That's called f average. That's the average height of that curve. And if you believe that the two areas matched, then this area and this area are the same. And on the one hand, on the left, that area is integral from a to b f of x dx. But on the right, it's just b minus a, that's the base, times the height, which we're calling f average. So if you divide b minus a to the other side, you find out f average is nothing other than 1 over b minus a integral a to b f of x dx. So it's just the area divided by the base. That's all it is. The average height of a curve is area under the curve divided by the base. Okay, now ramp up that idea. We're going to try to draw an analogous picture here, and it's going to be a trickier picture, and I'm not even sure I can do it. If we ramp it up one variable, then we have a picture like this. You got some surface, z equals f of x, y. And it's floating in 3D space, maybe like this. And you're imagining it as floating over some region like this. So there's the region over which the surface floats. And you can see it's tall at some spots and it's shorter at other spots. That's y, that's x, that's z, like usual. And you could find the total volume under that surface. And you could compare that drawing to a drawing where the surface was just horizontal, constant height. So this one is just z equals c. And you could try to arrange c so that the total volume was the same on both pictures. So let's put in those axes again. So it's the same story as up here. Only up here we were talking about area. Now we're talking about volume, but if you were interested in the total volume under there, then maybe you're interested in all this. So it's kind of low underneath that little swale there, but that volume definitely sneaks up, and you're going to get some all the way up into here. You can't see it, it's obscured, but you got a lot of volume under there. And if you want that to match this perfect, nice, easy prism shape where the height is the same everywhere, then you could arrange for it to match by putting the height of that rectangular prism at just the right spot. And that spot is called f average. And so we have the same story on the one hand. On the left, the volume is the double integral over the region R of whatever the function was with respect to area. So we're calling R this region down here. On the other hand, on the right, it's nothing other than area of the base times the height, which we can call f average again if we want. Or in other words, if you wanted to compute the average height of a function, it's just 1 over area of the base times the volume. And so this idea is the takeaway in 15.3. If you want the average height of some wavy surface where it's tall in some spots and short in other spots, just find the volume and divide by area of the base. And that's it. 15.3 is just a quick stop to say, hey, look what you can do with some double integrals. You can find the average value of some wavy surface, the average height of some wavy surface over regions in the complex or in the XY plane. All right, so that's it for 15.3, just a very small handful of suggested problems. Make sure you feel good about setting up average value. In the end, it's going to boil down to just being able to do some double integrals. And we'll talk on Monday. See you then. Bye.